Rao Bhim 7.6 Orthogonal and Unitary Matrices. Definition 7.6.1, we call a matrix orthogonal if it is square, it's a real matrix, and A transpose A equal to I. And it is called unitary if it's a square, complex entries, and A star A equal to I. You must understand that a real matrix is also a complex matrix, and A star A means it is transpose and complex conjugate. That is equal to I. So if you are working over the complex field, then any real matrix which satisfies this condition also satisfies this condition. Now there is an important intuition behind such matrices that we have to first understand, and we shall take as our example only the orthogonal case. Suppose we take any O and B of the vector space, which we take in this example to be R2. So these are of length 1 and this angle is 90 degrees. Then if I take these two vectors side by side as columns, then you will get an orthogonal matrix. So orthogonal matrix is basically equivalent to O and B. Now why is that? That is pretty easy to see. I call this A. Now I have to check that A transpose A is equal to identity, which means I put them down horizontally and then again vertically. Now when I do this matrix multiplication, what am I doing? I am basically taking this times this. So think of them as partition matrices. So it is this times this, that is the dot product of this and this. And this is supposed to be 1, which means the norm square of the first column is 1. That is, this vector is of length 1. Similarly, when I look at this one, it is the norm square of this entry. So that also has to be length 1. Now, why is this 0? This is because if I take this and dot product with that, that gives me this entry, which is 0, meaning that these two things are mutually perpendicular. And of course, if this is 0, and I also know that this is 0, which is not saying anything fresh in this 2 by 2 example. So this and this inner product is also 0. Now, this also tells you something interesting. If I take A transpose, that will also be identity, because A transpose A is identity means A transpose is just A inverse. So any orthogonal matrix you see is also invertible. As a result, you can pre-multiply or post-multiply with A inverse. So I could as well have taken A transpose equal to identity. So this condition packs two types of things. The diagonal entries tell you that the lengths are 1, and the off-diagonal entries tell you that they are mutually orthogonal. In other words, O and B's and orthogonal matrices are basically equivalent concepts. This is stated in terms of vectors, and this is stated in terms of matrices. Now, all this thing is over the real field. If you work with complex field, then orthonormal basis will be equivalent to a unitary matrix. Here, of course, we are working with the so-called canonical inner product, that is the usual dot product in case of R, and in case of complex numbers, the usual dot product, which is given by, if I have two vectors u and v in Cn, I am defining their dot product as summation ui vi bar. Now, whenever someone gives you a matrix A, there are two ways of looking at it. The first is as a collection of vectors. And we saw just now that if this is an orthogonal matrix, if I consider it as a collection of vectors, that collection forms a O and B. Now there is another way by which you can also think of a matrix as a linear transformation. So it is interesting to explore what is the linear transformation that is affected by an orthogonal matrix. Again, we shall be specializing to only orthogonal matrices, that is over real field. We can have analogous statements for complex field as well. Such a linear transformation, quite interestingly, must be an isometry, which means norm of x must be equal to norm of ax. Now, why is that? This is pretty easy to see. I start with this, instead I start with its square. So if I take its square, I will just show that the squares are same. So this will be same as ax transpose ax. Remember, we are working with canonical dot product. Now this is nothing but ax transpose a transpose, this part, and I leave this ax as it is. Matrix multiplication being associative, I can of course freely do this first, and A transpose A we already know is the identity matrix, so you are left with x transpose x, and that is exactly norm square of x. So whenever you are multiplying a vector by an orthogonal matrix, you cannot change its length. Now if you think about a vector in R2, so your orthogonal matrix is 2 by 2, and this is your x, and you are going to transform it using an orthogonal matrix, then we know that since it's a linear transformation, 0 must be fixed, so this base must be fixed, and the tip moves in such a way that the length does not change. And you can very easily see that the only thing that you can do is rotate it around. So if you have to keep this fixed and only can move this tip, you can rotate it. Or you can also reflect it. So the rotation and reflection just by themselves do not make much difference when you are looking at a single vector. But suppose I have got two vectors. In that case, they are going to make a difference. Suppose I have these two vectors, and if I rotate, then this will always be like this. So this will always be to a little bit to in the counterclockwise direction of the red arrow. The black will be to a counterclockwise direction of the red arrow. But if I reflect, say, along this line, in that case the black arrow will come here and the red arrow will come here. So that's the difference between reflection and rotation, and these are basically the only two things that have this property of being an isometry, at the same time fixing the origin. If you do not need fixing the origin, then you can also translate. So here you are left with only rotation and reflection, and this gives rise to the very popular intuitive motto that orthogonal transforms are equivalent to rotation or reflection. Of course, this rotation and reflection intuition works only in R2 or in R3, but if you want to generalize it to higher dimension, then rotation and reflection is actually defined as orthogonal transformations. Now, my description is somewhat incomplete because what I showed is any orthogonal transformation is an isometry. It's a rotation or reflection, but I have really not shown the other way around. If I give you an orthogonal transform, if I give you a linear transform such that this result holds for all x, so I am giving you some linear transformation affected by some matrix A such that whenever you take norm of this, it is same as the original norm and it works for all x, then A must be orthogonal. Of course, I am working only with the real field. If you are working with the complex field, then you will replace this orthogonal by unitary. The proof of this implication is not at all difficult and goes like this. This condition, if I put a square on both sides, translates to this, much in the way we showed the reverse inequality. The reverse implication is that x transpose A transpose AX is x transpose x, and this holds for all x. Now just write this side as the identity matrix, x transpose IX. So here you have a matrix which happens to be a symmetric matrix, and here is another matrix which also happens to be a symmetric matrix. Now it is not very difficult to see that if for two symmetric matrices you have this equality, then those two symmetric matrices must be the same, and the way it is to be seen is by putting various particular vectors in place of x. So the technique is like this: you take x equal to, say, some EI. So if you do that, So I take x equal to ei, and you will get the various things that you need, and using the fact that you are working with symmetric matrices, you can show, I leave that as an exercise, it is not absolutely trivial to show, but possibly 2 lines of argument, that this implies that this is equal to that. Just remember that we need symmetry of these 2 matrices. If the 2 matrices are not symmetric, then we cannot come to this conclusion. As a little hint, I can tell you that you first put x equal to ei's to show that the diagonal entries match, and then later you have to put x equal to ei plus ej, and that will show, after you have shown that the diagonal entries match, this will show that the ijth entries also match. So this equivalence is now completely proved. So we see that if I start with some vector x and I apply some orthogonal transformation to that, the vector that I will end up with will be a vector which has, of course, the same base, because 0 remains 0, something which has same length. Now we can, of course, ask the opposite question. It goes like this. Suppose I give you an x, and instead of giving you ax, I give you some vector y such that length of x is equal to length of y. Now my question is, can you come up with an orthogonal matrix such that if I multiply x with that matrix, you will come to y? In other words, my question now is, does there exist an orthogonal matrix A such that y is equal to ax? If I give you any 2 such vectors, can you do it? Now intuitively that seems obvious, because if I show it in R2, I can always rotate it like this. And there is yet another way. I can take this line, the perpendicular bisector, and I can do a reflection. So x goes to y and y goes to x. The question is, can you always do it in any dimension? And the answer turns out to be yes, you can do it both as a rotation as well as a reflection. Now one way of doing this reflection is given by the so-called householder matrix. Example 7.6.3. In this example, we start with a unit vector in Cn. The norm is 1. The norm means the usual canonical norm, that is u star u equals 1. We define the householder matrix as H equal to I minus 2 u star. Let us clearly understand the structure of the matrix. I start with the square matrix, the identity matrix, then I have this column vector and then this row vector. U star is the row vector. So this product, the product of these 2 skinny vectors, is actually a big fat square matrix of the same size as this. So H here is actually n by n. Now this example claims that this matrix will be both Hermitian and unitary. The fact that it is Hermitian is just obvious, because if you take H star, then I star is I itself, and minus 2 comes out, it's just a real scalar. Now when you take star of this u star comes here as u, and this u goes here as u star, so it remains the same. So H is equal to H star, and we have proved that this is Hermitian. The fact that it is unitary is not at all difficult to prove. Since it is a square matrix, we have to show that H star is identity, but H star is same as H, so we have just this. Now if I multiply, I will get something interesting. 2u star, and I follow it up with another I minus 2u star. Now when I just do the product, I will get some simplification. I get 4 terms, I minus 2u star, again minus 2u star, plus 4 u star, u star. Now it is here that I use the fact that u star u equal to 1. I can see that I have got a u star u here, so this is simply 1. As a result, I get minus 2u star, minus 2u star, plus 4u u star, all these things just cancel out, and I am left with simply the identity matrix showing that this H is unitary. Now I said earlier that Householder matrix reflects one vector to another vector of the same length, so it is as if I am putting a mirror here. Of course, the mirror is along a hyperplane, then reflection of x is y and reflection of y is x, and this matrix will do that. However, this matrix has no x or y in it, it has some u. So the way I relate this matrix with this reflection here is by taking u equal to unit vector along x minus y. So you take x minus y divided by its norm, and then you get a unit vector, so it satisfies this condition, and then you define h using that, and you will very easily see that if you take u like this, then hx equals y and hy is actually equal to x. And since it's a unitary matrix, it is basically rotation or reflection. In this case, it is more like a reflection, but of course in higher dimension, it is difficult to say what is rotation and what is reflection. Now for this to work, of course, I need x and y to be distinct, because otherwise this will be 0 and I cannot divide by its norm. If x and y are the same, then of course it is just trivial. If you want to take x to y and y to x, you just take the identity matrix, because x is same as y. Now this Householder matrix has many uses. One of them is to compute what is called the QR decomposition, but this is not the right place to discuss that.